Unit 5, Thermochemistry, pages 27 to 32. What causes a heat of reaction? So we have to look back at potential energy and recall that an apple stored at a height of h has a potential energy, and whenever it falls, it turns into kinetic energy. In order to climb up the stairs in a building, we must do work against the force of gravity. The energy of work required to climb the steps is converted into potential energy as we move higher up the steps. Suppose we use street level as a reference point and assign it a potential energy of 0. The decision makes the basement level have a negative potential energy and the floor have a positive potential energy. So here's street level. We're going to have potential energy 0, and so the higher up you move on these stairs gives you a positive potential energy or more actual potential energy. But if you consider going down to a basement, then you're moving to a negative potential energy. So it's going to require energy either way to go up the stairs and down these stairs. This is a release of energy going down these stairs. The x-axis of the graph below shows the distance between two magnets. On the far right, there is no force between the magnets because of the large separation. Suppose we label this 0 potential energy. As the magnets are brought together, the magnetic force gets stronger. The potential energy becomes negative. The existence of the force between the magnets means that energy is required to pull them apart. So here you have a 0 potential energy, and your magnets are close to one another, and so we're going to need energy in order to pull them apart. But if there's a little bit of distance between them, then we have potential energy that is between them, the potential for them to pull back towards one another because they are magnetized to each other. Chemical energy. The energy stored in chemical bonds is a form of potential energy. The chemical bond is analogous to two magnets. The chemical bond is a force holding the atoms together. To break the bond and pull the atoms apart, it requires energy. So breaking bonds requires energy. When energy is supplied in the form of heat, it is called the bond dissociation enthalpy. Bond dissociation enthalpy. So here you have a chemical bond, and there's potential energy in this bond. And if you manage to break them apart, then that energy would be released. So we need energy in order to break them apart from one another. We have to put in the energy to pull them apart. And then when you do, heat is required to break the bond. And so you have an endothermic reaction, or a positive delta H. Endothermic, heat must be absorbed in order to get from here to here. So the heat of reaction, which you're going to see represented as delta H of reaction very often, when a reaction takes place, energy is required to break the bonds of the reactants. Energy is released when new bonds are formed to make the products. The numbers above each bond represent the bond dissociation enthalpies in kilojoules per mole. Bond dissociation enthalpy equals the energy to break the bond. So here, if you have 2H2 plus O2 yields 2H2O, then if we write them out with their Lewis structures, here's my 2 hydrogen diatomics, and it takes 436 kilojoules per mole to break these 2 hydrogens apart from one another. And so we would actually have that amount times 2 here, total, and we would add the amount of energy it takes to break apart these 2 oxygens, which is 495 kilojoules per mole. The total energy it takes to break these guys versus the energy it takes to break the products, which are going to be water. And so each of these oxygen-hydrogen bonds takes 463 kilojoules of energy in order to break them apart. And we have 2 waters, so that value would be times 4 for our products. The heat of chemical reaction represents the combined efforts of energy supplied for breaking these bonds and energy released for bond formation. The energy is supplied in the form of heat at constant pressure, so it's called the enthalpy of reaction. For this reaction, the heat of reaction will be, the delta H is going to equal the hydrogens 436 times 2, 436 times 2, or you could say 436 for this hydrogen, and then times 2, the coefficient, plus 495 for the oxygen here, and there's only 1 oxygen, so times a coefficient of 1. And we're going to do minus the products 2 times, I apologize, it's going to be 4 times 463, and the reason it's 4 times that is because it's the amount to break each oxygen and hydrogen bond, and there are 2 of them in each water. This is going to be why it's important to draw out the Lewis structure in order to determine how many bonds you have and how many are going to be broken and formed. So we're going to do minus the 463, and this math right here is going to equal our delta H for the reaction, which is negative 485 kilojoules per mole. Note the use of positive energies for bond breaking because energy is required, and the minus for the bond formation because energy is released. The total net enthalpy for this reaction is delta H is negative 485 kilojoules per mole. The minus sign here indicates that the overall reaction is going to release energy in the form of heat, and so the reaction overall is exothermic. Heat of phase transitions. So this is going to be changing from solid to liquid to gas. In the solid phase, the particles are held in fixed, rigid positions. When a phase transition occurs from the solid to liquid phase, energy is supplied in the form of heat to overcome intermolecular forces in the solid. The added energy allows the particles to move against the intermolecular forces so the particles in the liquid can flow. Added energy means the delta H is positive. The reverse phase transitions, like liquid back to solid, is going to release energy, which is going to be a delta H that's negative. Energy must be removed from the liquid to allow the solid to form. So here it is in a diagram where you have solid and you have to add energy in order to melt it into a liquid, and you have to add energy to it in order to get it to vaporize from liquid to gas. And so going from solid to liquid to gas is going to be a positive value of delta H, or an endothermic process. Phase transitions that require energy to overcome intermolecular forces have positive values of delta H. Energy supplied in the form of heat is enthalpy. So solid to liquid to gas, liquid to gas are all going to have positive delta H values. Remember, solid to liquid melting is called the delta H of fusion. Liquid to gas is called the delta H of vaporization, and solid to gas would be the delta H of sublimation. And then the reverse, if you take the reverse of these processes, then they're going to release energy and have negative delta H values. Phase transitions that release energy have negative values of delta H. During phase transitions, sublimation, melting, and boiling, the added heat is used to overcome the intermolecular forces. And temperature remains constant during the phase change. So here's where you have solid, and you're going to heat the solid so it's approaching melting, and then once you get to this point right here, now the solid begins to melt. And notice the temperature remains constant throughout the process of the melting. And here is where we would see our delta H of fusion in play. Then we would continue to heat the liquid, so here we're in the liquid phase, and as we get to the boiling point, when it begins to boil, the temperature is going to remain constant, and here we have our delta H of vaporization in play. And then once we get to the end here, we have officially changed from liquid to gas, and so now we are just heating up the gas. During the heating portions of the curve, the added heat increases the energy of the motions of the molecules and temperature increases. So that's here, here, and here. We actually have a temperature increase. Here and here, the heat is being used to overcome the intermolecular forces binding the liquid and the gas, binding the solid and the liquid together. Note card for this section. Chemical energy. Energy stored in bonds is potential chemical energy. Bond is a force holding the attraction together and requires energy to pull it apart. When heat is used to pull bonds apart, it's called bond dissociation enthalpy. The delta H of a bond, or of a reaction, is going to be equal to bonds broken minus bonds formed. Heat of reaction are combined effects or net energy of bond breaking energy, which is always endothermic, and bond forming energy, which is always exothermic. When you have a phase change, you're going to change from solid to liquid, and it's called the delta H of fusion. When you have a change from liquid to gas, it's delta H of vaporization, and changing from solid to gas is called the delta H of sublimation, which is a combination of these two values.